Let's talk about what a neural network really is and how it works from the ground up in a way that makes the intuition and the mechanics line up naturally. At the highest level, a neural network is just a machine for learning a function from data. We give it inputs, it produces outputs, and we want those outputs to match reality as closely as possible. Instead of writing rules by hand, we let the network adjust itself by learning from examples. To make this concrete, imagine trying to predict something simple, like whether an email is spam. Each email can be described using numbers. How many links does it contain? How many capital letters? How often certain words appear? So already, the problem becomes numerical. We take numbers in, and we want a number out, maybe 0 for not spam and 1 for spam. Now let's zoom in on the smallest unit inside a neural network, which is called a neuron. A neuron takes several input numbers and produces a single output number. Suppose the inputs are x1, x2, all the way to xn. Each of these inputs has an associated weight, w1, w2, all the way to wn. The weights represent how important each input is. What the neuron does first is form a weighted sum. It multiplies each input by its weight and adds everything together, then adds one extra number called a bias. So mathematically, we write this as z equals w dot x plus b, or explicitly, w1 x1 plus w2 x2 plus plus wn xn plus b. This number z is not yet the final output. Next, we pass z through an activation function. The activation function squashes or transforms the number in a non-linear way. This step is crucial because without it, the entire neural network would collapse into a single linear equation, no matter how many layers we add. A very common activation function is ReLU, which simply outputs 0 if z is negative and outputs z itself if z is positive. So the final output of the neuron is a equals max of 0 and z. That is one neuron. It is extremely simple, but when we connect many of these together, powerful behavior emerges. Now let's stack neurons into layers. The first layer is the input layer, which just holds the input numbers. Then come one or more hidden layers. Each hidden layer takes the outputs of the previous layer, performs the same weighted sum and activation process, and produces new values. Finally, the output layer produces the network's prediction. What is important conceptually is that each layer learns a new representation of the data. Early layers learn simple patterns. Later layers combine those patterns into more abstract ones. For example, in image recognition, the first layer might detect edges. The next layer might detect corners and textures. Deeper layers might detect eyes, ears, or wheels. The final layer combines all of that to decide whether the image is a cat, a dog, or a car. Now let's talk about how the network actually learns. Learning happens through a process called training. Training always follows the same loop. First, we do a forward pass. We feed an input into the network, let it flow through all the layers, and produce a prediction. Second, we measure how wrong that prediction is. This is done using a loss function. The loss function takes the predicted output and the true output and returns a single number that represents error. For example, if we're predicting a number, a common loss is mean squared error, which is the square of the difference between the prediction and the true value. If we're classifying, we often use cross-entropy loss, which heavily penalizes confident but wrong predictions. Third, we adjust the network to reduce the loss. This is where backpropagation comes in. Backpropagation answers a very specific question: which weights cause the error, and by how much? The idea is to start at the output layer, see how the loss changes when the output changes, and then propagate that information backward through the network. Using the chain rule from calculus, we compute gradients, which tell us how sensitive the loss is to each weight and bias. Once we have these gradients, we update the weights. We do this using gradient descent. Each weight is nudged slightly in the direction that reduces the loss. The size of this step is controlled by the learning rate. So the update rule looks like this. New weight equals old weight minus learning rate times the gradient of the loss with respect to that weight. This process repeats over and over. We show the network many examples. Each full pass through the dataset is called an epoch. Over time, the loss decreases and the network's predictions improve. At this point, it helps to look at a concrete example. Consider predicting house prices. The inputs might be house size, number of bedrooms, distance to the city, and school quality. The output is a single number, the price. Initially, the network's weights are random, so its predictions are terrible. But after seeing many houses and adjusting its weights, it learns that size usually increases price, that location matters non-linearly, and that features interact in complex ways. Eventually, it produces reasonable predictions for houses it has never seen before. Now consider a classification example, like cat versus dog images. Each image is just a huge vector of pixel values. A convolutional neural network processes these pixels using specialized layers that exploit spatial structure. The same training loop applies: forward pass, loss computation, backpropagation, weight updates. After enough labeled images, the network learns to recognize visual patterns that distinguish cats from dogs. Once training is finished, we move to inference. During inference, we freeze the weights and only perform forward passes. The network no longer learns, it simply applies what it has already learned to new data. To summarize the big picture, a neural network is a layered collection of simple functions. Each neuron performs a weighted sum followed by a nonlinear activation. Layers build increasingly abstract representations. Learning happens by comparing predictions to reality, computing error, and adjusting weights to reduce that error. With enough data and the right structure, neural networks can approximate extremely complex functions. That's the core idea behind how neural networks work.